Hope everybody's having a great time. My name is Marshall Clow. I am going to be talking about hardening your code today. But before we get started, let's check a couple things. If you have a phone, please mute it. If you have a phone. Is there anybody in this room that doesn't have a phone? One. Wow. Anyway. If you have questions, put up your hand. If you can, please get to a microphone and ask it so that the recording will pick it up. If you don't, I'll repeat it back. This talk is called Hardening Your Code, and the idea about it is that there's a set of techniques that you can use to make your code better. I'm not going to be showing template metaprogramming. I'm not going to be showing really hardly any code at all. I'm going to be talking about techniques for making your code better, making your code have less defects. I was talking to somebody this morning, and they gave me a great analogy. This is like brushing your teeth and flossing. Well, you really know you ought to do it, okay? And you don't always do it. No, at least I don't. And so I'm going to encourage you to floss and go visit the dentist twice a year and all those things. Many of these things I suggest, you're going to say, well, yeah, I already do those. Great. I'm hoping that if you guys are all up on modern development techniques, you'll walk out of this room in an hour and say, wow, that was a waste of time. I do all that stuff. Hopefully, though, I got a few things that you can add to your regime. So let's start. It's a dangerous world out there, okay? It's a dangerous world for software. Creak. Maybe I'll stand still. There are people actively attacking code. Basically, people run in environments you don't control, you don't envision. There are 2 billion cell phones, 3 billion cell phones in the world running applications, running software, and you can deploy on a huge number. If you write for Android, you can run on 500 different models of phone, including phones that you've never seen, that you don't know how they work or what they look like. And sadly, good methodology is not enough. If we were all perfect and we followed best practices and all that stuff, we would write code without bugs. But everybody makes mistakes. Just in the security area, okay, secure communications area, in the last, say, 9 months, what have we had? Heartbleed. GNU TLS bugs stretching back 10 years. If you follow Apple, go to fail. And none of these were people being malicious. It was people making mistakes. The Heartbleed thing was is an implementation mistake. The go to fail was a failed merge. These caused a lot of trouble. And the other thing that is we tend to build big systems these days. We have better tools than we did 20 years ago. We build bigger systems. It's hard to keep all the details in your head. And so people make mistakes. They don't consider things. So the question is, what can you do to increase the confidence you have in your code? What is it that make your code objectively better? And make you feel like, yes, you believe your code is better, and you can demonstrate that your code is better. And I'm going to talk about several techniques here. And some tools that will help you with all these techniques, okay? So let's just dive right in. Remember your history. We have a whole class of tools for this. We call them version control. I bring this up not because I think there are too many people here who are not doing version control, but every now and then I run into somebody who says, what's version control? And it's like, oh, please. First step, right? Set up a version control system and use it for your source code. And actually, it's really amazing how many places version control works really well. I have friends who are web developers that I've got them on version control, and they can go back to a previous version of their website. I was talking last night with somebody about a package called GitRC. which basically installs a Git repo in /etc/rc on your Unix system so that every time you make a configuration change, it gets logged and it gets put in a version control system. I don't know if you guys have spent any time editing Unix configuration files, but what I always end up with was, dang, this worked an hour ago. What did I change to break it? Anyway, version control lets you go back in time to where you were an hour ago, a week ago, a year ago. It lets you try things and say, oh, that didn't work out, and roll back. It lets you remember how you got to what you go back and look at your history and your comments about that, and you can remember releases. There's a lot of version control systems out there, right? The popular ones these days are Git, Mercurial, Subversion. There's a whole bunch of other ones. I'm not going to say they're all the same because they're not. Each of them has different sets of advantages. But frankly, the differences between all the version control systems pale between the difference between having version control and not having version control. So to a first approximation, any of them is good. I mean, they're all better, way better than none. But do a little research, pick a good one. Okay. War story. This is not one of my war stories. This is from a blog from Eric Raymond's blog. I don't know if people are familiar with Eric Raymond. He's been doing open source for a long, long time and acting as an advocate. This is a blog, actually, a blog entry came out like 2 weeks ago. He was working on a chunk of software, and it stopped working. Some of his tests were failing. It's like, oh, dang. And he said, okay, well, I'll just revert my last change. Tests were still failing. And the problem was that the failures were conditionalized on a particular set of input data. And he hadn't been using that input data before, which was why the tests had been passing up into a certain point. And so he said, uh-oh, reverted back to his last release and tested, and they passed. And he was like, oh, good. So now it's like, okay. My users are okay. I know this bug isn't in the last revision that I shipped to them. Now I just have to figure out what it is. And he used git bisect. How many people here have used git bisect? There we go, a fair amount, like a fifth, maybe. So basically what git bisect does is you give it a test, a script, a program, and say, this is how we tell if the bug exists. And you say, at this revision in my source control history, this passed. And at this revision, it failed. And git bisect will automatically do what you would think to do manually, right? Go to the revision in the middle, check it out, run the test. Did it pass? Oh, good. Then move forward until it fails, move backwards until it fails. But it's just going to go, it says right here, this commit, this change was the one that caused this test to start failing. And at that point, finding it is much, much easier. You're not looking at 2 weeks worth of changes or something. You're looking at one small change, supposedly small change. I'm sorry? As long as you don't have a dependency outside the version control system, yes. But the point is that if you don't have a version control system and you run into this problem, you're pretty much screwed, okay? You go and you get the tar archive of your last release and you try it, and you say, oh, good, it passes. And then you look at your current source code and you say, you're in for a night of debugging, trying to find out what's wrong. And you will find it, but it's much, much harder than it would be otherwise. Okay, automated tests. Yeah, automated tests. Have a test suite, run it often, add to it whenever you can. This is, to me, this is just like so amazingly useful that it's uncontroversial. And yet I run into people who don't have test suites. The cool thing about about automated tests is that you have confidence in your code. You say, okay, I didn't break anything every change. You want to run the test suite before you check anything in. If your test suite is running fast enough, you can make a simple change, run the test suite, make a simple change, run the test suite, and you never get very far off of good. If you talk to the test-driven development people, what their suggestion is for doing development is write a test, watch it fail, write some functionality, write a test that shows you have missing functionality, watch it fail, write the functionality, run the test, watch it pass. I find that hard to do for new functionality, but it's really good for when you have a fairly stable code base and you're fixing bugs and so on. So I have seen this a lot, but I don't have a test suite, and it sounds like a lot of work. And the answer is, yeah, it is a lot of work. Writing a lot of tests is hard. I mean, they're not hard. In general, they're not hard, but writing tests is a lot of work. Okay? True, but like a version control system, having some tests is better than having no tests. Having more tests is better than having some tests. The goal is you want to have a test suite that is complete. So you can start small. Write a test. Okay? Pick some place in your code, some functionality in your code that you're worried about whether or not it works correctly. Write a test. Write another test. Add to it. Yeah, if you're sitting in a boarding meeting and the presenter is droning on about stuff you already know about, write a test. Just think about what part of your code makes you feel uncomfortable, like you're not really sure about it. Write a test to test that part of your code. Okay, what kind of things should you test? You want to test normal operations, all right? You want to have confidence that when your code is called with sane inputs, it does what you expect. Edge cases, places that you want to think this is a little tricky. Okay, error conditions. You want your code to return errors in some cases. Now, really, error conditions, that's a hole with no bottom. You could spend the rest of your life writing tests to test error conditions. Okay, so you got to use some judgment there. What are things that can happen? So an example, right? Suppose you have a sort routine. Okay, you have a sort routine. What kind of tests do you want about that? You should pick an unordered data set and sort it and verify that the result is sorted. Right? Pick an already sorted data set. Make sure that it sorts. Pick a data set that's in reverse order. Make sure it's sorted. A data set where everything is equal. Right? Pick an empty data set. Pick a data set with one element in it. Pick a data set with two elements in it. Maybe powers of 2, depending on the algorithm you're using. Powers of 2 plus or minus 1. You get the idea. I mean, the idea is just to make sure that it's a robust piece of code. Okay. What's next? Somebody reports a bug to you. What do? You write a test. Okay? This is where I am completely behind the test-driven development people. Write a test. Watch it fail. Fix the bug. Watch it. Run the test. Watch it pass. Now, what has just happened? You know you fixed the bug because you watched the test pass. You add the test to your test suite. That bug's never coming back. Or actually, let me rephrase that. If that bug comes back, the test will fail and you'll know it. You won't get bug reports from the field. I thought you fixed this bug. And you go and look and somehow it's due to somebody making a change over it or something that it's come back.
Find a test that doesn't work.
Right. Yeah, we were talking about that beforehand. Yeah, sometimes you find somebody was saying that they tried to augment a test and they added it and it wasn't failing. It started failing and it's like, what did I do? And it turns out that the test was testing the wrong thing or it wasn't getting run or something like that. Okay, but again, The idea is that this is a testing infrastructure, testing suite is not something that's really ever done. On the other hand, it's not something you have to work on all the time, right? As you add new functionality, you want new tests. Right, why are they important? They give you confidence in your code. They give you ability to change your code without fear. I've worked in several places which practiced what I call fear-based programming. Oh, we can't change that. It might break something. Anybody ever hear that from people, from your managers? Yeah. Oh, no. If you have a test suite that you're confident in, the answer is, yes, I can change that, and I can run the tests, and I can be confident that I haven't broken anything. How do you get confident in your test suite? And the answer to that is you try to write tests that cover all the functionality of your software. How can you be confident that you've succeeded? How do you be confident that your code is good enough to ship? Yeah, you guess, okay? You assert that it's good enough to ship, and this is the same kind of thing. You have to make a judgment that your test suite are good enough, are comprehensive enough, I guess is a better word than good enough. There are code coverage tools that will tell you that that your test suite covers that covers some percentage, 99%, 98%, 99, 97%, whatever, and that helps you feel that you have covered a lot of your code. I tend to go more as a functionality-based thing, is all of the functions are tested. But then again, I work on a standard library implementation. I have a 1,000-page specification that says exactly how things are supposed to behave. This is almost an ideal case for a test suite because I can look at the specification and write the tests. Other times, not so much. I have a comment here about enables refactoring, right? Refactoring is what? The ability to change the implementation and the structure of your code base without changing the functionality. How do you test that you don't change the functionality? You run your test suite. You had a question. Your test should be, yes, your test better be simpler than your code. Yes, I agree and disagree, because what you really want to have, in my opinion, is you want to have lots of simple tests. And the tests in the aggregate may actually be more complicated than your code, certainly may be larger than your code. But each individual test, small and simple, yes. I could go on for quite a while about refactoring.
Marshall?
Nope.
Question?
A question over here, sorry.
Or comment, actually. The one thing I've recently come into really love this, and the one thing that's given me confidence in my tests is that they break a lot. And that feels good because I found something. The other thing that I really like is when I break a test, but the test was wrong because I realized I really did change the semantics of something through a feature. And it satisfies me to see the precise tests that break that are the ones that you would expect to break. And I felt great when that happened.
Yes. Yeah, that's a really nice feeling when you change something and the tests fail because you changed it, but you changed it on purpose, and then you have to go fix it. You have to go update your test, not fix your test, update your test. The other thing is, in an ideal world, right, which we all live in, right? This is a great ideal world. Your tests are your release criteria. If it passes all your tests, your code is good enough to ship. That's hard to get to. Okay, I know a few projects that work that way. That if it passes the automated tests, then it's good enough. Absolutely. The comment is that it's easier with a library rather than an application, and I'm absolutely correct. You are 100% correct. When you have to do user interface and interaction like that, it's a lot harder to automate the tests. Okay. leaving tests aside, compiler warnings, okay? One time at my current job, I was working with another group, and they handed me a chunk of code that they wanted me to augment, so I tried to build it, and it came up with like 180 compiler warnings. And I said, hey, what's up with these compiler warnings? And they said, they're just warnings, ignore them. No. Who cares about compiler warnings? I do. You should. The compiler is telling you that there's something here that looks odd, okay? Compilers are not perfect. And again, in our ideal world, compilers would be perfect. They'd only warn on, they wouldn't actually have warnings, they'd have errors. But in any case, if you have, right, so you build your program, right? And you make a change and you build your program again. And the first time it had 100 warnings. And the second time it had 101 warnings. What's the odds of you actually picking that warning, that new warning out? Pretty much nil. But if you build it the first time, it has no warnings, and you build it the second time, it has one, you say, oh, I got a new warning. Let's go see what's up with that. So it's really hard to find a new one if you have a lot. Toy example, right? Unsigned. Takes an unsigned. If foo is greater than 0, return foo. Otherwise, return 1, 2, 3. Most modern compilers will warn on this. They'll give you something like, warning, comparison of unsigned expression greater than is always true. Why? Because unsigned numbers are always greater than or equal to 0. Okay? This code is not incorrect. It's perfectly valid, in this case, C code. The compiler is happy to generate code for it. It's just the person who wrote this code probably didn't mean that. They didn't mean to write if true, return foo, else return 123. The compiler is telling you something's going on, something looks wonky here. Okay? So here's a trivia question, right? What is the difference between greater than 0 and not equal to 0 if you're dealing with unsigned types? I heard it down here. The answer is nothing at all. Greater than 0 and not equal to 0, it's the exact same set of values are true and false for that. Okay? The compiler may actually generate a different instruction. It may generate a not equal instruction rather than versus a greater than instruction, but the results are always the same. So here's a case where the compiler is telling you that there's just, I don't think this is what you meant to say. You know? That word. You keep using that word. I don't think it means what you think it does. Anyway, you can test with 2 different compilers or 3 different compilers because different compilers have different implementations. They warn on different things, and you get a lot wider coverage with multiple compilers. That being said, staying at 0 warnings with on multiple compilers can be hard because sometimes they warn on different things, and you might have to do some refactoring of your code to get it into a state where everybody's happy with it. You have to decide if that's worth it. Okay. Sometimes compilers are just flat out wrong about warnings. Okay, here's a long blurb of text. This was written by a friend of mine on a private mailing list talking about his work on some large product that you have certainly heard of, put on by a large company in the Bay Area whose buildings you have almost certainly flown over if you've flown into San Jose. Big green buildings just down by the airport. Anyway. But we're not saying who. And we're not saying what product. Anyway, he said when he started working on this product, a full build gets thousands of errors. And he and one of his coworkers spent, a year or 2 in their spare time just looking at warnings. Every time they went into a source file and it built with warnings, they said, okay, we're going to get rid of the warnings in this source file. And he said it took 2 years, okay? But they have And they have data on bug reports from the field and crash logs and so on, and they found that the amount of crashes and bug reports has gone down significantly since they've done this. Correlation is not causality, right? But that's the way to bet, okay? These two are probably related. He said it took part-time work a couple years, but now they're at 0, and staying at 0, here you go, at the bottom, staying at 0 is way easier than getting to 0, because warnings don't just appear, right? People make changes, and they introduce new warnings. Anyway. Okay. Let's talk about static analysis. Static analysis is basically a way of reasoning about your program, automated reasoning about your program in an attempt to find bugs. And basically the way it works is that you take a program, you replace your compiler with a static analysis tool, it builds some kind of representation of your program, and then it reasons about it. It tries to prove things about it. There are several commercial products. The three large ones that I know about are called Clockwork and Fortify and Coverity. There are several open source implementations. Clang has one built in. Visual Studio, not open source, but they have a static analyzer. There are other ones. But they all work in a similar manner. Here's an example. Okay, we have function 1 that returns a string. Yeah, it should be const, but then that line was too long for the slide, so I took the const out. Okay, and then we have this thing that calls strlen on this, and you say len calls getString of x. Okay, most static analyzers will pop up on this, and they will say, what will they say? Will say this string, which is passed to len here, that you got from getString, it could be null, and you can't call null on strlen. Let me try that again. You can't pass null to strlen. Okay? And it's really nice when it says, look, you have a failure path in this code. The other thing that static analyzers will do is local reasoning. They will show you your function that is, say, this long, and they say if you take this if, and the false branch of this if, and you get to right here, and you use this local variable, which you never initialized, because you initialized it conditionally in some places, and you missed one path. Those are great things. I like static analysis tools. I like the idea of static analysis tools actually more than I like the implementation of most static analysis tools. They are heavyweight tools. The commercial ones are are enterprise tools. And my definition of enterprise tool is when you try to find out how much they cost, you get a message, a salesman will call you. But they're expensive to run. They take a lot of CPU time. Okay? They think hard about your program. They're noticeably slower than a compiler. They tend to have false positive rates, high false positive rates, because because they're reasoning about the program, and they do it not at runtime, so they don't have a lot of information about what inputs you get and so on. They have to reason a priori about how the code is structured. That being said, they do find a lot of bugs. Dynamic analysis. Okay? Dynamic analysis lets you basically build an instrumented version of your program that you never ship. Okay? So you don't worry about lots of things about it, but you build it and then run tests, whether your automated test suite, some other tests, whatever, and report when things go wrong. Okay? Real simple example, right? You build with assertions enabled. That's an instrumented version of your program. It's got assertions in it. And when one of your assertions fires, you say, oh, I have a misunderstanding. Something's wrong here, whether it be the assertion is wrong, okay? Or when I wrote this code, I didn't understand the problem, or I made a coding error, or something like that. That's an example of dynamic analysis, or just testing. Debug mode. Lots of libraries, lots of compilers, tools have debug mode that add extra checking in there. These are all good for finding things. Again, the key is that you don't ship these, right? These are for use for you internally. Microsoft has a debug version of the C++ standard library that's very helpful here. Sanitizers. Kostya gave a talk yesterday about sanitizers, and I'll talk a little about that. Basically, the way the sanitizers work is that they're usually implemented by the compiler vendor. You build an instrumented version of your program. They insert calls and checks into your program, and then you run your tests, and they go off. There are, as far as I know, there are 4 at the moment, probably more to be planned. Address sanitizer, undefined behavior sanitizer, memory sanitizer, thread sanitizer. Address sanitizer first shipped as part of LLVM 3.3 and GCC 4.8. UBSAN, the undefined sanitizer, is part of LLVM 3.4 and GCC 4.9. And MSAN and TSAN are part of LLVM 3.4, but are still experimental, I believe. So the goals for the sanitizers are that they have very few false positives. Goal is none. Okay, that every time something goes off in a sanitizer, it is a real bug. And it can report a misbehavior as it happens, when it happens, rather than the static analyzers, which are are doing things in an abstract sense. They're examining the code and thinking about what could happen when it was run. Because this does at runtime, you can get stack crawls and things like that, which is really nice for finding exactly where things went wrong. Okay, using address sanitizer. Basically, the way you use it is you build your program with -fsanitize equals address, and it gets passed both to the compiler and the linker. I ran this on, this first link here is a deployment report. I ran this on the libc++ test suite about a year ago. Excuse me, it's a year and a half ago now. And the libc++ test suite at the time was about 4,300 tests, and it found 3 bugs. It also uncovered a limitation in address sanitizer, but that's something else. Found 3 bugs. I mean, there were more than 3 instances of address sanitizer going off, but it turned out to be 3 bugs. There was 1 bug in the library that manifested itself probably a dozen times. It was a bug that we would never have found otherwise, because there was a case where the IOStreams code was allocating a 0-byte buffer when you created a stream, and then under some circumstances would write a single byte into that buffer. Okay, on the test system on macOS, the minimum allocation is 16 bytes. It was harmless. Okay, it did not corrupt anything. It didn't, it didn't cause any problem. When you wrote the second byte to the stream, the buffer got reallocated to a reasonable size, and so you'd never actually see it. Wouldn't cause any problems on macOS on the test system. But if you ever moved it to another system, libc++ is supposed to be portable, and you move it to another system where the underlying memory allocator has a different behavior, you get memory corruption, you get crashes. So it was great to find this. And ASAN just picked it right up and said, right here, this is the problem. We also found 2 bugs in the test codes. And that's a point that I want to make, that sometimes you have to worry about bugs in your test code. The bugs in the test code were of the form of passing a set of data into, in this case, it was into some random number generator, or passing a set of addresses to write random numbers, and it was the start of the array and 2 past the end of the array instead of 1 past the end of the array. There was that +1 there that shouldn't have been there. Anyway, really, really nice. Again, remember I said early on, how do you increase the confidence in your code? Doing this exercise not only fixed a couple bugs, but gave me a lot of confidence about the libc++ code. It just made me feel that the libc++ code was at the base was really solid. It had been written by somebody who really, really was concerned about correctness. And I can say that because I didn't write most of it. I don't know if Howard is here, but he did a great job. Also, if you, the link at the bottom is an announcement from the Mozilla Security Bulletin, and it talks about some remote code exploits that they had found in Mozilla, and basically credits the Google security team and Address Sanitizer for finding them. Address Sanitizer has been a boon to people writing web browsers because, frankly, web browsers have pretty much an unbounded input space. You can send almost anything to a web browser, and people do. And if you run it with Address Sanitizer enabled, you can find out immediately if you write off the end of an array, or you get a use after free, or you double delete something, or.
But only 3 out of 5 browsers use it.
Well, that sounds like a toothpaste ad from when I was a kid. 3 out of 5 dentists recommend. Only 3 out of 5 browsers use it. But I would guess that that the Internet Explorer people do not, because I don't think ASAN has been available on Windows for very long, or even if it is available yet. I know the Chrome people do, and I know this was a Mozilla thing, so I know the Mozilla people do, and the Safari people do. Yeah, the WebKit-based browsers or the Blink-based browsers tend to do that. But I don't think that it's really, I don't think it's a function of what web library you use. It just happens to work out that way. Yes, Kostya here. I mean, how many people went to Kostya's talk yesterday about the sanitizers? Okay, about 40%. I'm going to keep talking about the sanitizers then. If everybody had gone, I could skip some of this, but no. Undefined behavior sanitizer. Okay, I have another talk about undefined behavior and the perils that it can lead to. But I only got 20 more minutes, and that's an hour talk, so we're not going to go there. Needless to say, the C and C++ languages have a definition of undefined behavior, and compilers know this. And they make code generation decisions based on your code. Basically, they can assume in many cases that undefined behavior won't happen because, if it does, it's undefined behavior. It's not wrong. Okay, in my undefined behavior talk, I spent a bunch of time pointing out that once you have undefined behavior, there are no wrong answers. There's nothing, you can't say my program is misbehaving because you have undefined behavior. There's no correct behavior. But anyway, so these are some examples of undefined behavior. Signed integer overflow. Unsigned integer overflow actually is defined behavior, but signed integer overflow. Indirecting through null, indexing off the range of the ends of array. There's a whole bunch of other things. But, and John Lakos touched on this in his talk on Wednesday when he spelled my name wrong. But that's okay. Anyway, UBSAN catches a lot of these, the language-based undefined behavior. And it tells you exactly where it was. This was my favorite, was load a value 1, 2, 3, which is not a good value for type bool. Yeah. And you look at that and you say, yeah, why would that Boolean have a value of 1, 2, 3? And you go look at it, and you look at the code, and you stare at the code, and all of a sudden, oh, yeah, it's just wrong. That's the answer. It's wrong. And then you go and fix it. Yeah. Index 40 out of bounds for array of type blah, 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 10. Really nice to know. Anyway, I ran this on the libc++ test, libc++, and this is the blog entry talking about the results. This is about a year ago. I need to go back and run through it again and see if I've introduced any more bugs. But it finds all sorts of interesting things. Okay, I'm not going to talk about MSAN and TSAN because I haven't used them. But if you're doing a lot of threading code and you're on a system that TSAN supports, it will help you find race conditions. And MEMSAN helps you find reads of uninitialized memory, which is technically undefined behavior. But okay, fuzzing. Fuzzing is a technique that has come into popularity in the last few years, especially in the security arena. It's basically it's a way of automated testing for systems when the problem space is very large, or you have you're not really sure how to comprehensively test your system. And basically, you take a sample input to your program and then you mutate it according to some criteria, and you change it to be not quite valid or invalid in some ways. And usually you end up with thousands or hundreds of thousands of test cases because the idea is you're trying to generate some kind of coverage thing. And then you feed them into your program and wait for it to misbehave. There's a link here for talking about doing this. This is, again, a great thing for browsers, okay? Because the inputs for browsers are fundamentally unbounded. And there are a lot of browser manufacturers out there who are doing this. The nice thing about, oops, wrong way. The nice thing about dynamic analysis and the sanitizers is they work really well with fuzzing because, pick ASAN, okay? Because ASAN goes off immediately when your program misbehaves. You can generate a bunch of fuzz tests and feed it to your system and find out immediately when something goes wrong. If you don't have something like a sanitizer or a debug build or something like that, frequently what you're looking for is you're looking for your program to crash or give wrong answers. And if it does that, then you have to go investigate. But if you have an instrumented thing, whether with a sanitizer or a debug build or somewhere, that it can point at just right here, an assertion went off, or ASAN fired, or UBSAN fired, or whatever, you say, oh, I know exactly where something is wrong. Something has gone badly wrong right here, and then you've cut your debugging by 90%, 95%, 99%, which is great. Okay. Okay, wrapping up. All these things, you can start small. Well, the static analysis stuff tends to be have a big startup. And source control pretty much is all or nothing. Or you should be using source control. Okay, you should be going to the dentist every 6 months, right? You should be using source control. Tests, start small. If you look at the test, say, okay, I want to have a test suite, and you look at it and you think about it, you realize this is a daunting task. Don't get discouraged. Start. Take another step. This gentleman right here in the green shirt, he's writing a test. Because he knows all this. No, I'm kidding you. But the point is that you can start small and just keep going. Okay? And a test suite really is not a get it done kind of thing. It's good to have a good one today, make it better tomorrow, and so on. The dynamic analysis stuff, just you can. What I do is I run the test suite for libc++ every night. My machine back at work wakes up at midnight and runs the tests 8 ways. It runs it 32-bit, 64-bit, times 3, C++03, C++11, C++14. It runs it with UB sanitizer enabled. It runs with address sanitizer enabled. And then every morning, I come in and I have a summary of the results. And I glance at them and say, yep, same as yesterday. good. No unexpected successes, no unexpected failures. That takes, 5 minutes, 10 seconds, somewhere in between, and then I start up on my work. But I have this baseline of confidence every morning that code's in good shape. Okay. Questions? Can we all come to the mics? Claire is running to the microphones. Yes.
So, wonderful, really, really good stuff, really agree. Just a comment in terms of putting into practice, moving towards getting people using Test Suite. Because a lot of the later things only had value if you had good Test Suite coverage in the first place. And when you've got a large volume of code that doesn't have tests, understanding how to introduce them can be really hard. And just something I learned recently was if people get a really good foundation of the solid principles of object-oriented design, and there's a brilliant few-hour Pluralsight course on that.
Okay.
It shows examples of refactoring to get rid of concrete classes low down. And I suspect that's probably obvious to a lot of people here, but if there's anyone you're working with that doesn't know that, for me, that gets people over a really, really large hard hurdle of where do I start? It just made so much stuff make sense from which then you can start. It's an enabler, really, to start actually adding the tests.
Right. Okay, so I'll take a look at the Pluralsight course. Also, out here in the bookstore, there's a book, a Martin Fowler book called Working with Legacy Code. Okay. The most interesting part about that book for me was in chapter 4, where he puts down his definition of legacy code. His definition of legacy code is code without tests. Because you're deep into, as I said, fear-based programming then. I can't change it, it might break. Kostya.
Thanks for advertising Fuzzing and dynamic tools mix. It's really amazing how efficient it is. And I want to recommend a secret sauce to this pair, which is code coverage.
Okay.
What my colleagues at Google found that if you add code coverage feedback to fuzzing, it gives 2 times more bugs to you.
Okay.
You run the fuzzer with dynamic tool and with coverage, and if a newly generated test has some new coverage, like it goes into a new part of your program, you add this test back to the main corpus of tests, and that is like a positive feedback or genetic algorithm to finding bugs, whatever. Use code coverage.
What code coverage tool should be used?
The question was, what code coverage tool do you use?
My colleagues are using code coverage tool built into Address Sanitizer, but you can feel free to use any tool.
Okay. Thank you. That's a great idea. I need to try that now. Over there?
Yeah, the discussion earlier about how do you get confidence in your test suite. One comment on that regard is, as you said, whatever your release criteria is, presumably you have some. If your test suite is working well, your release criteria should never find anything else, right? So as you start finding things in your release QA, pulling those back into lower tiers of testing is always valuable. We even do this in LLVM in terms of we have nightly test suite that take ages to run. Oh, they found a failure. Okay, add that to our fast regression test suite by making a narrower example.
Right.
The kicker, and I don't know whether you've played with this, Marshall, I haven't, but I keep hearing about it, mutation testing. The idea we could build something build it into LLVM where it mutates your conditions in your program, completely breaking the program.
Okay.
And if your tests find it, they're good. This helps you get things better than, say, code coverage.
Oh, interesting.
Code coverage only tells you the code ran. It doesn't tell you that it did the right thing.
Yeah.
It doesn't tell you that your
Interesting.
tests actually examined the output. So mutation testing is a way to test your tests.
I have not seen that. Okay, I'll take a look. Thank you. Charlie?
Yeah, code coverage seems to be a hot topic.
Yes.
In my experience, I found a cute, pithy remark about it. It can tell you how badly you're doing. It can't tell you how well you're doing. Okay, because all it tells you is you hit that function or that line of code at least once, but your code has this huge combinatorial complexity of paths you can take. So I've found that it's really good at finding holes in my test coverage, but once your code coverage gets up there, doesn't tell you that you're really doing a good job.
Right. Okay.
Right?
Good point. Thank you.
The one tool you didn't mention was continuous integration build systems. I think once you've got a test suite and sanitizers and stuff like that, and you're using multiple compilers, I think at that point you kind of need a CI system just to keep track of everything.
I do not disagree with that, but I didn't want to talk about this here because really that, well, not even that it's a whole nother talk, but it is more that the things that I have here are things that you can start as an individual in your company, okay? And a continuous integration setup kind of, you end up with a lot of infrastructure that gets built. And I like continuous integration structure. The LLVM project, for example, has a bunch of build bots that basically spend their entire day looking. Oh, it says check-in, great. I'm going to build, I'm going to run the test suite, and then I'm going to black the results into an IRC channel and blame the person who just checked something in because something failed. But I like those, but they're a lot harder to set up than starting to add tests or adding some more tests.
Starting to, yeah.
Yeah, I agree.
So Marshall, you mentioned fear-based programming, which I have participated in. And what I found is that unit testing is actually an excellent way to overcome the problem. That when I've faced something that has no tests, I've been afraid to refactor it. And an excellent way to start on the problem, both to understand what it is you're about to refactor and to have confidence in the results, is to start out by writing a bunch of tests for this thing. In the process of writing the tests, you understand what it is you're trying to work on. And once you do your refactoring, you can have some confidence that you probably didn't break most of it.
Yep, great point. Writing tests increases your understanding of the problem you're trying to solve. Absolutely.
I've now had 2 jobs where my first task was, we have all these compiler warnings, get rid of them. It is a nice way to touch all over the code base and start getting a feel for where all the code is, but it is several orders of magnitude harder to solve the warnings that someone else introduced, because you don't know what they actually wanted it to do.
Yes, it's true. The compiler is telling you, this is something odd here, and you end up with, well, what is this code supposed to be doing? Right. Yeah. Yes. Right. And I did not actually mention that in the section on the source control system. But yes, modern source control systems have an ability to go down to the line and say, who checked this code in? And yeah, it's usually called blame. Who is, SVN blame, git blame. And you can look and say, who checked this chunk of code in and when did they check it in? And it's like, oh, I look at libc++ code. Oh, Howard checked this in 4 years ago. Well, it's probably right. But yeah, and when I had the thing about getting rid of warnings, I mean, seriously, my friend, we'll call him Dave, because every Tom, Dick, and Harry is named Dave. Let's call him Dave. He spent a couple years at this, and it worked well for him. When you got rid of all the warnings, did you feel that the code was better? Absolutely. Do you have any objective evidence that the code was more reliable, smaller, had fewer bugs, any of that stuff? Okay. Should you map what unit tests it before you get rid of all? Yes.
Yeah, good stuff, Marshall. One other piece of this that I would bring up that's sort of correlative to the fuzzing is doing test randomization, especially if you have big suites of Google tests. Basically, we have a job, a nightly job in our CI system that basically randomizes all the seeds into the Google tests.
Okay.
And it finds a lot of it finds a lot of stuff.
There you go. So yeah, introducing, making your tests non-deterministic. If you can randomize the tests and still determine that you get the right answers. Okay. Any other questions? Gosh, just got another one.
A comment about compiler warnings. Even if your project is completely warning-free at some point, this is a constant fight, because compiler vendors keep adding new nice warnings.
Adding new warnings.
And this
Oh,
is an
yeah.
endless war. It never ends.
But you know what? The thing is that you hopefully your code quality is trending upwards, and that's really my takeaway. Is for all these techniques, you want to get the trend lines going up. That you have your code is getting better, the number of bugs is going down, and you feel better next week about your code than you did today. Next month better than next week. Next year better than next month. So, here I have actually a little bit of code that talking about getting rid of warnings. This is a chunk of code that that I wrote for Boost. It's real simple. It takes some value type and turns it into a number. It's supposed to be a character, 0 through 9, A through F. Okay? Real simple code. I cast it to a character. I check 0 through 9, A through F. Some compiler, we won't say which one, said, warned on this code. Control reaches end of non-void function. Okay? Compiler was wrong. There's no way to fall off the end of this function. Okay? It's return, 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 throw. But the compiler was warning on this, and I wanted to get rid of the warnings. So I said, fine. Return 0. And that shut up the compiler. Okay? It's like, dang. But you know what? Some other compiler said, you've got unreachable code. Fine. Okay, a little more refactoring. This generates basically the same code. If you crank up the optimization, the compiler puts the return value into a register, and really, there's not any difference between the first one and this one in terms of code quality. But this is just as clear, easy to read, and there are no warnings in this on any of the compilers. Okay, I preferred the first one. Okay, I thought the first one was perfectly clear, but actually no, because the compiler actually reduces this down to pretty much the same code as the first one. The difference is at is at 0, and the difference is in the source code. But a narrowing error on the. Oh, you're right. Yeah, it should be unsigned char. The thing is, though, is it's only returning 0 through 15. You're right. It should be unsigned char.
Couldn't you also, if you have a return on every if block, you could just move the throw outside of the else?
Could, but the compiler, the original compiler, the compiler that was wrong would still complain, even if the last. It was an old version of GCC. Anyway, so yeah, so everybody go out there, brush your teeth, floss, go to the dentist, right, and apply that principle to your code.